Hello, today we will talk about series and parallel AC circuits. When you combine series or elements that are connected in series when with elements that are connected in parallel, that circuit, the total circuit is considered a series and parallel AC circuit. The way to solve the impedance, admittance, all the characteristics that we've been learning is the same way. You find the parallel portion of it, you solve for it. You find the series portion of it, and you solve for it. So the goals are to be able to first determine what is the main characteristics of a series and parallel network and become proficient calculating the currents and voltages through the circuit, and also be able to solve for the voltage drop and the current through different components. So let's begin with an example. This particular case, we have that there's a voltage source and the voltage is 120 volts. This is similar to what we get in our place at home and at the office, etc., at school, so you can plug in the computer, and has a zero phase offset, has no shift on the incoming wave with the initial angle. It's just the energy coming through the transformer nearby and has no offset. So this wave is going through a resistor. This could be a laptop or it could be some sort of component. It's a passive element. And then it goes in parallel to a capacitor and an inductor. So as you can see, we already know how to do this part, right? This part is going to be the impedance of these two elements in parallel. And after that, we can get a total impedance for those two elements, which then will let us compute the total impedance of the circuit by computing the impedance of the circuit in series for Z1, which is this resistor, and Z2, impedance 2, which is this parallel network. Okay, so to compute this, we already know how to do it. Notice that the first thing they ask is the total impedance. So the way I like to compute the total impedance is very straightforward. It's just 1 over square root. This is the general form of 1 over the reactance of the resistor plus 1 over the reactance of the inductor minus 1 over the inductance of the capacitor squared. Okay, notice that is not the capacitance of the reactance of the capacitor first minus the reactance of the inductor. No, this is the formula. It's the general form, and if you don't have one of the elements, then you simply ignore it. For instance, we don't have a resistor in parallel for this network, so this is going to be 0. If you type this in your calculator, which is 1 over square root of 1 over 3 minus 1 over 2 and squared, then you're gonna have that the answer is 6. So this total parallel impedance is 6 ohms. Okay, we have this, which is giving us here. Now, for this particular problem, we also need the angle, and computing the angle from this configuration is not as simple. Now, from experience, I know that there's a capacitor in the network in parallel, so it's going to be lagging 90 degrees. But the way to calculate that, it's much easier if you're using phasors. So another way of doing this is using phasors, which is simpler to find the angle, and you know that this is going to be XL times XC, reactance of the capacitor, over the inductance 3J minus 2J, right? Which is capacitance and inductance, no resistance. Therefore, this part right here, if I go to this part right here, if I follow this line here, is going to be the inductance is 3 ohms at a phase shift of 90 degrees, and the capacitance is going to be 2 ohms at a phase shift of negative 90 degrees. So notice that multiplying phasors is 3 times 2 equals 6, and 90 minus 90 is 0. But we have, this is in parallel, we have a denominator, and the denominator is going to be 3 minus 1, which is minus 1j, and j is the, you know that j is the imaginary axis. So if we were to draw this here, we have 0 in the real axis, we have 1 in the imaginary axis, which is because of the inductor, and then if we do square root of 0 plus 1 squared, this is simply 1, right? So negative 1j is the same as saying plus 1 at a phase shift of 90, right? Plus 1 because it's 3 minus 2j. So it's 1 at a phase shift of 90. Now, 6 from here, 3 times 2 equals 6, 90 minus 90 equals 0, and then we're going to have 1 over 90 degrees. 6 divided by 1 equals 6, and then 0 minus 90 is negative 90. So this is what we get right here. Since we do need the angle, the phasor approach is much simpler. If you only need the magnitude, then I like this approach much better because it's straightforward. So now we have the value of Z2, which is the network in parallel, and now we can do in series Z1 plus Z2, where Z1 is this resistor right here. So all we have to do is find the total impedance of the system, where Z1 is equal to 1 ohm and Z2 equals negative 6 ohms because of the 90-degree angle, correct? If it's positive, it will be plus 6 ohm imaginary. So computing this is very straightforward. We are gonna do the same thing. Total impedance equals 1 squared plus negative 6 squared, square root of that. This is going to be square root of 6 times 6, 36, plus 1, 37. So square root of 37 equals 6.08 ohms, which is right here. And then the angle is going to be 6 over 1 tangent inverse. So tangent inverse 6 divided by 1, 80.539 or 80.54. Notice that since we had a negative phase shift, then we keep the negative phase shift. Okay, so it's negative 80.54, and the way to compute that is simply, let me check something here. Correct. The way to compute that is, as we did before, let's see. To compute this, we're going to do tangent inverse of negative 6 over 1. This will give you 80.53. Excellent. So we have the total impedance, which is 6 ohms with a phase shift of negative or lagging 80.54. Now we want to know the current from the source. Since the Z1 and Z2 or both impedances are in series, then the current is the same for both elements. Therefore, we can apply Ohm's law for series in circuit or circuit in series for AC source. And in that case, we'll simply do the current equals the voltage, which is 120 volts with 0 degrees offset, and the total impedance, which is 6.08 ohms at a negative 80.54 degrees. So we simply do 120 divided by 6.08. This gives us 19.74, and 0 minus, so this is divided 0, this part right here, dividing factors, we know this by now, is 0 minus, and the value is negative, so negative 80.54, they give us positive. So there you go. The total current is 20 amps, almost 19.74 amps at a 80.54 phase shift. Okay, so now we also have to do the voltage drop through the resistor and the capacitor, the current through the capacitor, the power delivered, and the power factor. So notice the voltage through the resistor is just Ohm's law of the resistor. The voltage through the capacitor, since the capacitor and the inductor are in parallel, the voltage through the capacitor is the same one as the voltage through the inductor. The current through the capacitor, since the capacitor and the inductor are in parallel, the current through the capacitor is different than the current through the inductor. So let's find those things. First, voltage through the resistor, and for that we can use Ohm's law as well. So voltage through the resistor is the total current times the impedance of the resistor. The total current we just computed, and the impedance through the resistor is given the impedance of the resistor or the reactance of the resistor, excuse me, and then we multiply both numbers to get voltage drop through the resistor to be 19.74 at a phase shift of 80.5 degrees. The voltage through the capacitor, we mentioned that the voltage through the elements in parallel is the same for each leg or each branch, this being the capacitor and this being the inductor. So by computing the voltage through any of them, we know both because they're the same. So we can do Ohm's law again, and we simply have to do the total impedance of element 2 or network 2, which was computed here, 6 ohms and negative 90 degrees. So that's what we have here, correct? We have the current source times 6 at negative 90 degrees. So 19.74 times 6 is 118.44, and 80.54 plus negative 90 is negative 9.46 degrees. So this is the voltage going through the capacitor. Now, what is the current through the capacitor? So since we already know the voltage through the capacitor, we can do Ohm's law again, but this time we have to use the reactance or the impedance of the capacitor. So we have the voltage through the capacitor, which is the same as the voltage through the inductor because it's a parallel network, and we have the impedance or the reactance of the capacitor. It was given. So if you look at the figure again, it was 2 ohms is the reactance, and since it's a capacitor, then the impedance is the reactance at a negative 90 degrees phase shift. So the current is the voltage through the capacitor, which we just computed right here, and the impedance of the capacitor. Therefore, 118.44 divided by 2 is 59.22 amps, and negative 9.96 minus negative 90 is 80.54. Okay, so this is the current through the capacitor, 60 amps. That's a lot of current. You probably need a fuse or something um, on that network because it's a lot of current. Now they ask for the power delivered, and that is basically the power that is, if you notice, 19.74 is the power from the source. So power is I squared times R. So 19.74 amps squared times 1 ohm, which is the resistor, gives us 390 or 389 watts. And the power factor is nothing but the cosine of that angle that you're providing your power with. So the angle from the current source is 80.54, therefore cosine of 80.54 is 0.16.4. Oh, sorry, 0.164, which is a very small power factor. Now, in parallel, we can use Kirchhoff's law of voltage and current to find potentials. So if, for example, they tell you that they ask you, what is the potential between point A and point B for this branch? Of course, assuming that this is not, if this is ground, then basically this is 0 and this is 0. But assume that there are other elements over here, a motor, an inductor, a resistor. At this particular point, this voltage is not 0 and this voltage is not 0 because ground is far away from this point and from this point as well. Therefore, the voltage between those two legs or 2 points could be, you can compute it using Kirchhoff's law. And it's just like we see for DC circuits, the same thing. We know that the voltage drop between those 2 points, voltage AB, plus, and remember the direction of the mesh or the direction of the system of equations usually goes with, you choose the direction, but it's usually the same direction that it's clockwise, correct? And then you generally have negative close to ground, positive close to your source, and then the same here, negative and positive. So if you go with the clockwise direction that we assigned, we see that we'll go plus or positive, negative, and then you go negative, positive. Okay, so in other words, voltage AB is equal to voltage R2 minus voltage R1. Voltage R2 minus voltage R1, right? Or another way to see it is the voltage drop between A and B is the sense of the direction of my clockwise rotation is going negative first, and then positive is flowing the direction of the source. Then this is positive. And for our second resistor is going counter counter direction of the current for the resistor is going plus and then positive and then negative. So since it's going the opposite direction, this is going to be a negative. So the voltage from A to B plus the voltage R1 minus the voltage R resistor 2 must be equal to 0, and this is because of conservation of charges. All right, so if you do this for an example, and they tell you what is the voltage drop between, or what is the voltage potential between A and B here, and notice that the ground is far away from those points. If the ground was right there, if you put the ground right there, then it's going to be 0 because the ground is supposed to be 0 voltage. But there's a voltage drop here, another one there, and evidently the voltage at A is the same voltage that B because it's in parallel, but the difference between AB is useful because then you can know what is the voltage through each leg. So if you were to compute this, let's say calculate the current from the source and find the voltage from A to B. So the source, the same thing, Ohm's law. The current from the source is voltage divided the total impedance. The total impedance, very simple. We know that this part right here is in series, R1 with the inductor and R2 with the capacitor, so we can do that. They're in series, so it's simply 3 ohms plus 4 ohms. This is going to be 5 ohms at 53.33 phase shift. And this is, how do you know this? Because it's basically a resistor in the real domain and has a value of 3, and an inductor with a value of 4 in the imaginary domain. And when they meet, and this value is square root of 3 squared plus 4 squared. This hypotenuse is 5, which is the total impedance, correct? And then the angle is basically tangent inverse of 4 over 3, which in this particular case is 53.13 degrees. Okay, what about the second one? The second one is R2 minus, because the capacitor in series, 6 ohms. So 8 minus 6 is going to be square root, the total impedance, square root of a squared minus 8 squared minus 6 squared. So this is 64 minus 36 square root of that. And sorry, but then it's going to be squared plus squared. So this is 100, 64 plus 36 equals 100, and square root of that is 10, correct? Then tangent inverse of 6 divided by 8. Notice that the denominator is bigger, so it's going to be negative. It's negative 36.87. Okay, so we have computed the first impedance and the second impedance. In that case, to compute the total impedance, you simply have to add them up. Okay, in this particular case, they're not, you have to add them up using the rules of parallel circuits, right? So it would be 1 over square root, etc., etc. Okay, but in this particular case, they're not asking for the total impedance, they're asking for the current. And since the voltage through this leg is the same as the voltage through this leg, we can use Ohm's law at this point. And to use Ohm's law, we need to compute the total impedance, which we said that we can use Z1 and Z2 impedance from the first combination and impedance from the second combination, and they're in parallel. So if you do that, it will simply be Z1 times Z2. I'm talking about total impedance divided Z1 plus Z2. So this is 5 times, or 5 of phase shift of 53.13 times Z2, which is 10 at a phase shift of negative 36.87, divided by our 3 plus 8, which is 11 in the real domain, and 4 minus 6, which is negative 2j. Okay, so this is 50, denominator is 50, and 53 minus 36, that is 23, let's see, 53.33 minus 36.87, 16.46. 16.46. So the numerator is 50 with a phase shift of 16 positive 16.46, and the denominator is and we need to do the square root of this. So we will do square root of 11 squared plus 2 squared, and this is 11.18. Yes, 11.18. Okay, so the number is 11.18, and an angle of negative tangent inverse of -2 divided by, what is the resistance? 11. And that gives us negative 10.3. Negative 10.3 degrees. Okay, so the total impedance is 50 divided 11.18. So let's do 50 divided 11.18, which is 4.47. Yes, this is what we get here. Excellent. And the angle is 16 minus 10.3, which is 16 plus 10 is 26. There you go. So we get the total impedance, and then to find the current, we just need to do the voltage, which is 100 volts with no phase shift. All right, so 100 divided by 4.47 is 22.3, and 0 minus 26.56 is negative 26.56. So we found our current from the source. Excellent. Now the other question is find the voltage AB, and this is where we get to use the Kirchhoff's law. So to find voltage AB, we need to find the voltage through the resistor 1 and voltage through the resistor 2. Remember, because if we have a circuit where we have an element here and another element here, and we're saying what is the voltage between here and here, then plus minus, we need to do our clockwise rotation, and evidently we need to know, in order to find this voltage AB, we have to know the voltage through R1 or through Z1 and the voltage through Z2. In this particular case, the first two elements are resistors, so we just need to know the voltage through those resistors, but if they're inductors or capacitors, you simply compute the reactance and the impedance of those elements. Okay, so for the first case, voltage of resistor 1, what we need to do is, we know that there's going to be a division here because it's parallel. So even though the voltage is the same, the current is different. The current through this leg and the current through this leg. So coming from here is the current for the source. And in that particular case, we can compute the current through each leg using the impedance of each networking series. So we already have that. We said that the impedance of leg 1 is this part, and impedance of the second leg is this part. Okay, so we can find the current through each leg because of Ohm's law. And we say that the impedance through, remember, the voltage through each leg is the same, 100 volts from the source, but the current is different. What is the current? It's pretty easy. 100 volts divided by the impedance of leg 1, which we computed already. This will give us 20 amps at negative 53.13 phase shift. The current through leg 2 is 100 volts divided by impedance of leg 2, which is 10 ohms at negative 36.87 degrees. That gives us 10 amps at 36.87 degrees offset. Knowing the current through the first leg and the current through the second leg, we can compute the voltage through each element. So for the resistor 1, we simply do current through the first leg times the resistor or the impedance of the resistor 1. That is this value of 20 amps at negative 53.13 degrees times the value of the resistor, which is 3 ohms. That gives us a voltage of 60 volts at a negative 53.13 degrees offset. Through the second resistor, we have current through the second leg and the impedance of the second resistor. So we know the current of going through the second leg, which is 10 amps at negative of positive 36.87 degrees, times the value of the resistor, which is 8 ohms, which is right here. And that will give us 80 volts at a positive phase shift of 36.87 degrees. Now, to find the voltage between A and B, we know that the voltage magnitude is going to be the same, but there's going to be a phase shift difference, right? Because there are different elements here. You can have capacitors, inductors, etc. So what is that phase shift? For that, we simply do the Kirchhoff's law, which is voltage AB equals the difference between resistor 2 and resistor 1, the voltage drop through each element. And since we have those values, we simply do 80 volts at 36.87 and then the second element minus 60 volts at negative 53.13. If you turn these values into complex and imaginary or real and imaginary parts, you know how to do this by now, correct? This is the phasor, this is the magnitude, this is Z, and you do cosine of the angle for the real part, and the imaginary part is Z times sine the angle. So 80, in other words, let's do this part. So using your calculator, 80 times cosine of 36.87, that will give you 63.99 or 64. This is this value right here. And then if you do 80 times sine of 36.87, that will give you 48 positive. Since the angle is positive, you have a positive imaginary contribution. Then do the same thing here and use the negative angle to give you the imaginary part. Okay, so in that particular case, if you do the summation of all the elements, you get 64 minus 36 is 25, and 48 plus 48 is 96. Therefore, turning this into phasor again to know the difference between A and B, this will be square root of 25 squared plus 96 squared. Let's do that. 25 squared plus 96 squared. 99.20. Okay, so the actual voltage is 99.2. And the phase shift is the tangent inverse of 96 divided 95. 75.4. So what I get is that this is the magnitude and the angle is tangent inverse of 96 over 25, and that gives me 75.4 degrees. All right, so the voltage difference between A and B, or the voltage between A and B, is 99.2 at 75.4 degree phase shift. So that tells you that voltage potential between those two legs. Even though at this point is the voltage from the source, that is 100 at 0 degrees offset, and at this point is from the source as well, at 100 at 0 degrees offset. Why is this important? Because if you're gonna install a compressor, a pump, a motor, you need to know those phase shifts in order to have maximum performance. And a combination or an extension of serial plus parallel circuits is often called a ladder network. And if you notice, this is just basically the same configuration, but just with different details. For instance, in order to solve this circuit, you first have to do these two elements in series. Once you have those two elements in series, you'll do that combination in parallel. Then that combination in parallel will this in series, and then that combination in series will be performed with this in parallel, and then at the end you have this configuration in series. In other words, impedance 5 and impedance 6 have the same current through them, so they can have a total impedance called Z prime prime. And then at this particular case, you have Z prime prime connected to Z4 in parallel. So Z prime prime and Z4 in parallel form a single network that is in series with Z3. Then that is a single network that has is in parallel with Z2, and then that total network is in series with Z1, and that is what we have here. At the end, you can find the current source by doing Ohm's law of the voltage divided by the total impedance. And then you go back distributing the voltage and the current through each network. So evidently, once you have your current source and you want to know what is the current through leg 3 or current at node 3, you can do current divider rule, which is the current through the impedance, the second element, times the current through my second element, divided by the impedance of the second element, which you should know, and the total impedance of all this network. Right? Because if you remember, Z prime total is right here, and is this part right here in series, and then in parallel with Z4, and then in series with Z3. So all this part right here is the network configuration for Z prime total. And then what it's telling us is that to find the current at node 3, we have to know the impedance of element 2, which we should know because it's a passive element, the current from the source divided by the impedance of the second element, and the total impedance of Z prime. And total impedance of, oh sorry, it doesn't take Z2. The total impedance of Z prime is this guy. Alright, so Z2 times current source divided by Z2 plus Z total prime. That will give you current 3. And to find current 6, you can keep doing voltage divider, current divider rule, which is going to be similar. Z4 times I3 divided by Z4 plus Z prime prime, which is this part. Okay, so this is useful information that you should be able to write down and remember when you have ladder networks. Why do you use Z3 is because remember that at some point you assumed that these elements were in series, so the current is the same. So if you were to use Tinkercad, remember that you can go to tinkercad.com, which is from AutoCAD, and you can set up your AC circuit and analyze your voltage drops and your currents. So you can set up this circuit with a voltage source and sine wave of 10 volts, sorry, of 10 volts amplitude or peak to peak, and then 1 kilohertz frequency. And then you have these passive elements of R1 is 1.2 kilo ohms, R2 is 2.2 kilo ohms, R3 is 4.7 kilo ohms, R4 is 9.1 kilo ohms. Capacitor 1 is 4 nanofards, capacitor 2 is 10 nanofarads, and inductor 1 is 10 millihertz. If you were to compute or measure with oscilloscope the voltage from the source, which is this node and that node, notice that this is ladder network. The voltage from the source is basically, this is a little small here, but this is 20 from here. This is negative 20, this is positive 20. Therefore, the middle point around here is 10 and negative 10. So it's peak to peak, 10 volts. And then that is the voltage peak to peak from the source. And then if we were to measure the voltage from after or from this point to that point, basically the point from the source to the capacitor, it will tell us that now instead of 20 is 10 and little, so like around 5.7 and 5 negative 5.7. So this is very useful because you can see the voltage drop measured with the oscilloscope through your sine waves, and you can compute your answers with Tinkercad and compare it to your solution on your notebook. Now, going back to how to apply the concepts, if you look when you go to your house or to your school or to your office, whichever place you would find typical outlet, you'll see that typically there are going to be 3 orifices or 3 little holes. And that is because, as we mentioned before, for 120 RMS, you have L1, neutral, and ground. Okay, so this is ground. It's a problem right here. Then we have L1, and we have neutral or return. Excellent. So, for instance, you have 120 RMS socket, and then there's usually a 20 amp breaker installed either behind this element or at the panel board, and it will break the fuse or the breaker if the current exceeds 20 amps. Okay, and you can get more than 20 amps, say if you connect a microwave plus a little toaster oven plus a lamp, and if you keep connecting things, you'll draw more current. So for safety, there are fuses throughout the house because the idea is that you connect things at different places since you don't want too much current through a single wire because that can catch on fire, etc. So if 12 amps go through your socket, actually it starts way before this. So there's going to be the power plant or whoever is getting your electricity, and then it's going to those huge towers on the highway, and then they get to the transformer by your neighborhood, and then the transformers to your house, and then as we saw before, each wall socket will have a configuration of 120 or 240, etc. So once you get out your voltage to the wall or to your socket, then you get your 12 amps. Say, for example, that you're using the microwave and the toaster oven connected to this configuration, or you're using some type of appliance that is using 12 amps, like a dishwasher or something. So it's going to 12 amps. 12 amps are going to be used by your appliance or whatever you're using that requires 12 amps. And then it's closing the circuit back to the grid. Okay, so this is the concept of the power how to deliver power to your school, to your house, etc. The ground is very important because it's what keeps the potential or the circuit from being to having a cut or a shortcut, and it's extremely important to make sure that the things you connect to ground are properly insulated and that it's not missing the prong. Sometimes old houses didn't have this, so people would have to remove, which that was, it's not a good idea to remove that prong because the socket doesn't have the third hole. In that particular case, do not use an appliance that requires ground connected to the prong, because those prongs are there for applications that require high current. So this is another example right here. If, let's say, for the power equation, which we know one way to calculate or to compute power is the voltage times the current, or the same thing can be from, if you have a resistor, you know the resistance is I squared times the resistance. If you know the voltage, you use this equation. If you know what is the load, you know this equation. You know you can go from one to the other using Ohm's law. But using the power equation, which is voltage times current, draw, and for example, under normal operations, you have a power of or appliance that consumes 1.2 kilowatts or 12,000 watts. What is the current used? So just by using this equation, we have 12,000 watts and it takes 120 RMS. Then what is the current? Very easy. 1200 divided by 100, 1200 divided by 120 will give us around 10 amps. So this is a little high because usually a toaster is not 1.2 kilowatts, it's much smaller than that. But it could get to that point if it's a large toaster. But the point is that there's still a breaker on your panel board or by your socket where 20 amps will have the limit of the current applied to the toaster. So if there's something wrong with the toaster and it starts getting more current, it will break the fuse and it will prevent from, you know, causing an accident or an incident. Notice that this is telling you that it's 12 ohms. So we could have also do, we can do 10 squared times 12, 1200. So since they already give you that the normal resistance of this equipment under nominal conditions is 12 ohms, then P equals 10 squared, current squared, times 12. This is 100 times 12 equals 1200. So it does much. So you remember that these two equations are equivalent. But if you look at the circuit, you have your positive leg or your L1, usually called hot line, going into your system, and then your neutral taking it back to the socket. In this particular case, they're telling us that this appliance, this equipment, is probably only having two connectors. Doesn't have a third connector. That means that this one goes from L1 to neutral, and then there's a ground internally here, and L1 goes, or neutral goes to ground. So some connectors only have two prongs, but for high current applications, for high electrical current applications, there should be 3 prongs: hot or L1, neutral, and ground.